This is the first video in a series to help students understand the difference between the four kinds of chemical reactions. We used to call this a chalk talk when we were using blackboards. We're going to start with one of the simplest types of reactions, simple decomposition and simple synthesis. So you might see on a worksheet, identify by type the following two reactions. Solid barium carbonate, when heated, will give you barium oxide, solid, and carbon dioxide gas. The second reaction, we know that when copper sulfate, the anhydrous copper sulfate, is mixed with water over a period of time, it will become the blue copper sulfate pentahydrate crystal. So let's look in turn at how we might consider this, and we'll also, in the course of our discussion, look at the heating and dehydration of hydroxides. So let's start with the barium carbonate decomposition, and we need to visualize what's happening on the atomic level. Look at the reaction and identify the two types of compounds you see here. Barium carbonate is an ionic salt. That's the reactant. Barium oxide, one of the products, is also an ionic oxide. Both are ionic compounds, but carbon dioxide, as with carbon monoxide, is a molecular compound. You may remember it's a linear compound. If we visualize this, we look at the products first, and you can see carbon dioxide, the molecules on the top, and then a little simulated crystal of barium oxide down below with the O2- and the Ba2+ interspersed so that the crystal hangs together with plus-minus attraction. Let's now look at the reactants that it came from. The original barium carbonate reactant had a barium 2+ ion and the carbonate, which is a 2- ion, polyatomic ion. Can you see that the only change in the barium is which -2 ion it is bonded to? In the barium oxide it's bonded directly to the oxide ion, but in the barium carbonate it's bonded to the carbonate ion, which is also on -2. Therefore, the charge on the barium ion remains 2+, so there is no oxidation, no loss of electrons, there's no reduction, no gaining of electrons. The charges are the same, and therefore the carbonate decomposition is a simple decomposition. Now let's, in passing, consider the decomposition of hydroxides because it's analogous. Let's identify in the reaction magnesium hydroxide, solid, when heated, will give you magnesium oxide, solid, and water vapor. Of course, you see the magnesium hydroxide and magnesium oxide are both ionic compounds. Water is the molecular compounds that's being driven off. Now let's look at the products first and then the reactants. Here are the products. You see the magnesium oxide below, and we've just shown one of the magnesium oxide units. And then the water vapor that has come off of it. When you look at the reactants, you see there's really no difference in the ions there, except that the water product is taken from the magnesium hydroxide by taking one of the hydrogens and attaching it to one of the oxygens, and then it's driven off as water. So the magnesium charge remains 2+, so there is no oxidation going on there, and there's no reduction going on anything. You're just moving the atoms around, moving the ions around. So hydroxide decomposition is simple. Now, not all hydroxides will decompose with heat. Sodium hydroxide, for instance, will not. So if you want to answer the question, how is a hydroxide decomposed? The answer is it's always a simple decomposition, but if there's no way to get water out of the compound, then there will be no reaction. Now let's look at the decomposition of hydrates. That's not one of the reactions we looked at. But if you remember the decomposition of copper 2-sulfate pentahydrate, you notice that the hydrated salt has water molecules embedded within the crystal structure of the salt. And so when heated, the vibrational energy of the water becomes so high that the water turns into a gas and is released from the crystal. The charge on the copper ion, which started off as 2+ here, remains 2+ in the anhydrate. So no oxidation or reduction is occurring, and hydrate decomposition, whether it's copper hydrate or cobalt or magnesium sulfate, it's not a problem. It's always a simple decomposition. Now, let's turn it around and consider the synthesis of hydrates. We know that you can mix the anhydrate copper sulfate here on the left with water and restore the blue crystals of the copper 2 sulfate pentahydrate that you see a picture of on the right. This reaction is the reverse of the dehydration, and you see it up on the top shown with liquid water being mixed with the anhydrous copper sulfate on the left. The charge on the copper ion, which starts off as 2+ in the anhydrous salt, remains 2+ in the hydrated salt. There's no oxidation or reduction going on there. Therefore, the hydrated crystal synthesis is a simple synthesis. So in this video, we have gone over simple decomposition and simple synthesis with these two examples, and we've also talked about the dehydration of hydroxides, and that it also is a simple decomposition.